Hello, so it's me again. As I promised, I'm gonna make a video on one example of finding the area, the exact area of the function on some interval. So this will definitely help you with the last two problems on your homework, which is due on Thursday. Okay, so let's recall the definition of the Riemann sum. So the area under the curve over an interval is equal to the limit of the left approximation, which is likely to be the same as the limit of the right approximation. Okay, so let's just do one example to see why this holds. So the example is find the area under the function x squared over the interval 0 to 1. So we're going to first find a generic expression for Ln and Rn respectively. And then we'll let n goes to infinity and see that this will give us the same result. Okay, so what is the idea here? So let's first graph the function roughly. You don't have to do this when you do your homework, but I just want to show you the graphical intuition behind this. Okay, so x squared looks like this. Okay, and we're interested on the interval 0 to 1. Okay. All right. So what does the definition of Ln say? Okay, so if we cut the interval 0 to 1 to n small pieces, okay, then the width of each small piece is equal to delta x, of course, but in particular, in this case, we have 1 over n, okay? So the total length is 1, and we're subdividing this into n pieces, so each piece has length 1 over n, okay? Okay, so what's the left approximation using n rectangles with the left endpoint? So this is equal to f0 times 1 over n plus f1 over n times 1 over n. Okay, so 0 is the first left endpoint, and 1 over n is the second left endpoint. All right, plus all the way to which point? So what is the last rectangle? The last rectangle is this one. I can see. Let me see if I can draw this. Okay, so this is a tiny rectangle. Okay, and if you think about this, you will see that the left endpoint is n minus 1 divided by n times the width, which is 1 over n. Okay, and clearly we can just take out the 1 over n, of course, and what we got is just the sum from f0 to f n minus 1 over n. Okay, another way to write this using the sigma notation that you just learned, this is equal to the sum from 0 to n minus 1 of f of I divided by n. Okay, easy. So this is not done yet because we don't want this f here. We just want the precise expression. So this is equal to 1 over n. So let's recall what is f again. F is x squared, right? So this is equal to I over n squared. And simplify this further so we can break this parenthesis and put square here and square on the bottom as well, and then move out the n squared on the bottom. And what we're gonna get is 1 over n cubed of the sum from 0 to n minus 1 of I squared. All right. So yeah, I'll leave it like this. Okay. So what about Rn? Okay. Rn, the procedure is exactly the same, except for that we're now using the right endpoint for each sub-rectangle. So this is equal to, so what's the first right endpoint? It is 1 over n, right? So we are going to use f of 1 over n times the width of the first rectangle, which is again 1 over n. And similarly, 2 over n times the width 1 over n, and so on. And what is the last right endpoint? Is clearly just 1 or n over n, right? So in this case, we're going to use let me use another color. In this case, I'm going to draw this very carefully. In this case, we're using this rectangle, okay, with the right endpoint on the curve. Okay, so the right endpoint is just 1, which is 1 n over n times 1 over n. Great. Okay, so doing the same thing as we just did for Ln, this is equal to the sum from I equals to 1 to n of I squared. All right. So what about the limits? The limit as n goes to infinity of Ln is equal to what? Is equal to the limit as n goes to infinity of 1 cube 0 to n minus 1 I squared. Okay. So this is the same as the limit as n goes to infinity of n 1 over n cube times. So let's think about the first term of this sum. It starts with I being 0, but the first term is I squared, so it's also 0. So this is the same as I equals to 1 to n minus 1 of I squared. Okay, and you can see the formula from your book that the sum of this number, okay, this is equal to m times m plus 1 times 2m plus 1 divided by 6. Okay, so now let's apply this to this term, but this time the upper bound instead of m is n minus 1. So we're going to get, the limit, of course. We should never forget the limit. The limit as n goes to infinity of 1 over n cube of, so the first term is n minus 1, the second term is n, the third term is 2n minus 1, okay, plus 1 divided by 6. Okay, let's simplify this a bit further. So this is equal to the limit as x approaches to positive infinity of 1 over n cubed of n minus 1 n, and if you break the inside parentheses, you will see that this is equal to 2n minus 1 over 6. Okay, we can cancel this n with one of the n's on the bottom, and what we're gonna get is simply the limit as n goes to positive infinity of n minus 1 to n minus 1 of 6n. Okay, then let's recall what this number is. take the infinity, this is equal to 1/3. All right, so let me move this to the top, and let's compute the limit of Rn. Okay, so the limit as n approaches to infinity of Rn is equal to, we just copy down the expression for Rn, which is, wait, sorry, there is a n cube here, just as how we derive this n cubed for Ln. Okay, the sum from I equals to 1 to n of I squared. Okay, so we're going to do the same thing. We're going to apply the sum of squares formula and get 1 over n cubed of n plus 1 to n plus 1, excuse me, over 6. And again, n cancels with one of the n's on the bottom. So this gives us the limit as n approaches to infinity of n plus 1 to n plus 1 divided by 6n squared. That means a square here.